So pure rotational spectra is seen now. This is for vibrational, and pure rotational spectra is seen in the range of what? 10 to the power of 3 micrometers to 10 to the power of 4 micrometers. So in the range of this, we can see, uh, which is, we can be calling it as a microwave region. And also we can see in the case of the far infrared region. So that is in the range of 10 to the power of 2 to 10 to the power of 3 micrometers. So in both these ranges, understand, in both these ranges, this pure rotational spectra we can see. So in the pure rotational spectra, again, it can be applicable for only what type of molecules which are having the permanent dipole moment. Okay. So for the permanent dipole moment molecules only, we can able to see this pure rotational spectra. And that too, we will be calling it as what? Heteronuclear diatomic molecules. Heteronuclear diatomic molecules is nothing but which is having the two different atoms. Like examples, it has been given in book as a HCl, one of the example it is given, as well as the HBr. Otherwise, we can say that the CO, like this, we can see. So whenever this range, like CO2 molecule also, we can able to see this pure rotational spectra. So we can see in the case of the heteronuclear molecules, which are having the permanent dipole moment, whenever the light is observed, we are going to be see this spectra, and as well as the whenever it is emitting the spectra in the range of these, whichever we have mentioned, we are going to be see this rotational spectra, we are going to see. So in the case of the rotational spectra, we have seen this molecule as a rigid rotator we have seen. So which is, we got the frequency of radiation as nu is equals to h by 4 pi I into j plus 1 we have seen, and also allowed energy levels, otherwise observed energy levels in the case of the rotational spectra we have seen, like for j is equals to 0 to j is equals to 4 we have seen. Okay, that is about rotational spectra which we have. Now we will move to this vibrational spectra. So from where we are going to get this vibrational spectra also we have to see here. So now we'll see this vibrational spectra. So this vibrational spectra, you see. So as we know that again, this vibrational spectra is going to be get in the range of 1 to 100 micrometers. 1 to 100 micrometers, or we can say that 1 to 10 to the power of 2 micrometers region range we can see, which we are going to be call it as what? Near infrared region. Near infrared region. So in this region, okay, in this region, we are able to get this vibrational rotational spectra, or vibrational spectra we are going to be get here. So vibrational rotational molecular spectra, which is going to be arises from the transitions between the vibrational energy states. Transition between the vibrational energy states. Understand? Transitions between the vibrational energy states associated with the same electronic state of the molecule. Okay, and that range is going to be fall under this region, which we are going to call it as a like a 1 micrometer to 10 to the power of 2 micrometers range. You are going to be fall here. So like pure rotational spectra, the vibrational rotational spectra are obtained for only molecules having the permanent dipole moment. So for which molecules it is going to be get, as we have seen in the case of the pure rotational spectra, the molecules which are having the permanent dipole moment. So this is mandatory. So if you have a permanent dipole moment, then only we are going to get this what we call a vibrational spectra or vibrational rotational spectra we are going to get. So permanent dipole moment means this is you are going to be get in the case of which type of molecules? In the case of the heteronuclear molecules you are going to be get. In the case of the heteronucleus molecules only you are going to get this permanent dipole moment. As in the case of the rotational spectra is also applicable for only heteronucleus molecules, and as well as this vibrational spectra is also applicable for only heteronucleus molecules, because they are going to be possess permanent dipole moment, they are going to be possesses. So suppose if you take a homonuclear molecules, so like examples H2N2O2, whichever we are going to be have. So we are not able to see in the case of the homonucleus molecules, this vibrational spectra, we are unable to get this spectra. Only in the case of this, what we call heteronuclear diatomic molecules only, we can see this vibrational rotational spectra. So generally in the case of this vibrational rotational spectra, what happens means the heteronucleus diatomic molecules, whenever they are vibrating, okay, whenever they are vibrating, the molecules, whenever they are vibrating, which is accompanied by a what we call oscillating dipole moment. Okay, so suppose if you take two different atoms, heteronucleus one, they are separated by certain distance like this. Okay, they are separated by certain distance. So whenever they are vibrating, what will happens means this position of these atoms, they will be vibrating from that place to another place. From one, they'll be moving to there and again coming back to their same place. Like this, the vibration is going to be takes place. So whenever this vibrating molecule is accompanied by this what we call oscillating dipole moment. That means they will be oscillates like this. They'll be moving maybe to this place, okay, like this, and again this can be moved to this place. So from original place to this side or this side, whichever they are going to be vibrate. So whenever they are vibrating, it will be acts like a what we call oscillating dipole. So you are whenever it is oscillating, so you are going to be have the dipole moment, which we'll be calling it as a oscillating dipole moment. We are going to be called here. Okay, oscillating dipole moment we are going to be called here. So in this case, in the case of the vibrating what molecule if we take, so we will be calculating vibrational energy of a diatomic molecule. Here we are going to be calculate. Vibrational energy of a diatomic molecule. Vibrational energy of a diatomic molecule. Right. So in this, as we told that the vibrational spectra is going to be arises only for heteronucleus molecules, and whenever they are vibrating, the vibrating molecule, which is accompanied by oscillating dipole moment. So whenever it is oscillating, we can take that as a what we call as an harmonic oscillator. We are going to be take. Okay, the vibrating diatomic molecule can be taken it as a harmonic oscillator, we can say, and that harmonic oscillator possessing the frequency which is equals to nu is equals to 1 by 2 pi under root of k by mu or m we can represent here. Mu or m is nothing but reduced mass we are going to be called here. Okay, we'll be calling that as a reduced mass we are going to be called here. So suppose uh, if you take this diatomic molecules, so which is having two different atoms, as we know that this is going to be applicable for only heteronucleus molecules. So as we are having two different atoms which are separated by certain distance here. Suppose if you take this is one atom, this is another atom. So they are going to be separated by certain distance r we have been taken. Okay, they are separated by certain distance r. And as we know that these atoms are going to be vibrate, so they are going to be change the distance actually, which is called as the equilibrium distance that we are going to be taken as a RE. That means whenever these atoms they are vibrating, they'll be moving to above or below whatever it may be. So they'll be vibrating. So that distance we'll be calling it as the equilibrium distance RE. We are going to be called here. So therefore, initially the distance between them is R we have. So whenever they are vibrating, the equilibrium distance is given by RE. So therefore, the effective distance, which we can call it as a displacement, which we are going to be taken it as what? R minus RE we are going to be taken. The effective distance, that is the displacement for this atom is given by R minus RE we can take here. So now that the force in between them, which is given by general F is equals to minus Kx we have. Understand? F is equals to minus Kx. So here, F is right. So F is equals to minus Kx. So here we can write that as F is equals to minus K as it is, that is a force constant whichever we have. And in place of X, that is the displacement, we can write it as what? R minus RE we can write. F is equals to minus K into R minus RE we can write here. So that F is equals to minus Kx, and that will be equals to for one individual atom. So for different atoms, like we have two different atoms, one is having the mass of M1, here we have another, we have the mass M2. So for the first atom, we can write F is equals to this one as F is equals to minus K into R minus RE, and that we can write it as what? M1 for the first one, and D square R1 by dt square we can write, okay, for the first atom. And similarly, for the second atom, we can write that as what? F is equals to, we have same force constant and K, and the equilibrium distance is same for both the atoms, R minus RE. And for that one, we can write it as a D square R2 by dt square we can write here. So R1 is nothing but the distance from the center to this atom. This is what we have R1, and R2 is nothing but from the center to this another atom, the distance is R2 we have. So the total distance is R is equals to R1 plus R2 we have here. So for one atom, we have written F is equals to minus K into R minus RE into RE, which we can write it as a M1 into D square R1 by dt square. So that is for one atom. Another atom we have written as what? M2 into minus K into R minus RE into D square R2 by dt square we have written. So already we have seen that when we have studied in the last class for a diatomic molecule, the distance R1 can be written as what? M2 by M1 plus M2 into R we can write here. And similarly, R2 also we can write. R2 is equals to, we can write it as what? M1 by M1 plus M2 into R we can write. Understand? So now here, if you write this as in terms of mass, if you write this d square R1 by dt square. So d square R1 by dt square. So here we are going to get it as a d square by dt square into, in place of R1 what we have, like M2 by M1 plus M2 into R we have. So we can take this out, M2 by M1 by M1 plus M2 we can take outside. So it will be d square R by dt square we can get here. So d square R1 by dt square we have written as what? M2 by M1 plus M2 into d square R by dt square we can write. Similarly, we can write what we call d square R2. That is for the second atom, d square R2 by dt square as what we can write. Directly I'm writing here. That will be equals to what? M1 by M1 plus M2 into d square R by dt square we can get here. Okay. So we have got d square R1 by dt square we have got, and similarly we have got d square R2 by dt square we have got. So therefore, previously the equations whichever we have written here. So this equation, that is the force constant, force which we have written for first atom as M1 into d square R1 R d by dt square we have written. And similarly for the second atom, which we have written as F is equals to minus K into R minus RE, which is equals to d square R2 by dt square. So these two equations, we can write it as together as, in both the cases, the force constant, force is given by what? Minus K into R minus RE we can write here. So that will be equals to actually, what is that? Either we can have M1 into D square R1 by dt square, or we can write uh, M2 into d square R2 by dt square we can write. So both are same, like because if you equate these equations, like minus k into R minus RE is same in both the cases. So we can write that is equals to M1 into d square R1 by dt square, or we can write M2 into d square R1 by dt square we can write. So here if you combine those, we are going to get it as what like here I'll solve here, because we know that if we equate those, we can write it as M1 into d square R1 by dt square, which will be equals to M2 into d square R2 by dt square. Understand? Therefore, here, in this case, if I write what we call d square R1 by dt square value, d square R1 by dt square value, we can get it as what? M1 into M2, M1 into M2 by M1 plus M2 into, simply you'll get d square R by dt square you'll get. Understand? So similarly, this side also you'll get M1 into M2 by M1 plus M2 into d square R by dt square. So therefore, both are same we have got. So that we can write minus k into R minus RE is equals to what we can write? M1 into M2 by M1 plus M2 into d square R by dt square we can write here. Understand? So how we have got this? That is, by combining those equations, first equations, we have got this minus k into R minus RE is equals to what we have got? M1 M2 by M1 plus M2 into d square R by dt square we have got. Okay. So this we can write it as the top I'm writing here. Right. So that equation we can write it as what? So here I'm writing. So what we can write? This minus k into R minus RE, which is equals to this M1, M2 by M1 plus M2, whichever we have, we will be calling it as what? A reduced mass we are going to be called. What is that? Reduced mass. M1, M2 by M1 plus M2, we can be calling it as reduced mass. So which we can write it as mu, we can write. Reduced mass is equals to mu. Mu into, we have like what is that? D square R by dt square we have. Okay. So which is equals to mu is equals to, here in the case of this vibration, what we call no, this distance R is given by what? R minus RE. Okay. The displacement whichever we have, that is given by R minus RE. So we can write that as d square by dt square into, in place of R, what we can write? R minus RE, because the vibrating molecule, you'll be having effective displacement as R minus RE we have. Why? Because it can be moving, vibrating the molecule from original position to some other position and again coming back like that. So therefore, we can write that as what? D square by dt square into R minus RE we are going to be right here. So here, the value of, here if you write this, this is equals to mu into, we can write it as a d square R by dt square minus mu into d square RE by dt square we can write here. Understand? So if you separate this, we can write it as mu into d square R by dt square minus mu into d square RE by dt square we can write. So this entire value is equals to 0. Okay, because d square RE by dt square is equals to 0 we have. Since we can write this as value is equals to 0. So therefore, effectively, the value of this, we can write it as 1. Right. So we can write that as what? Which is equals to minus k into R minus RE is equal to, we can write it as what? Mu into D square R by dt square we can write here. Okay, this is the equation which we can write here. Okay, so this is actual equation. Me to the equation whichever we have, which is given in your book. So that is equal to minus dV by dr they have given. So don't write that equation. This is the equation 13.6 you can take. Okay, this is the equation you can write 13.6. Right. So now here the equation whichever we have got, the equation minus k into r minus re is equals to mu into d square r by dt square, whichever we have got. So this equation is similar to what we call simple harmonic oscillator. This equation is similar to simple harmonic oscillator. So for a simple harmonic oscillator, whichever we have, the frequency of vibration which is given by vibration here, which is given by nu. Nu is equals to 1 by 2 pi under root of k by mu, we can say that mu or m, whatever it may be, the reduced mass. Okay. So whenever this vibrating molecule is the diatomic molecule is vibrating, which is going to be produce the frequency of radiation, which is equals to nu is equals to 1 by 2 pi under root of k by mu we have. Okay. So far, whichever we have studied, this one is according to the particular classical mechanics, whichever we have. Okay. This is what according to the classical mechanics. That is the frequency of a vibration, new vibration we can say here, new vibration here, whichever we have, that is equals to 1 by 2 pi under root of k by mu. K is the force constant and mu is nothing but what? The reduced mass whichever we have. So this expression whichever we have got, this is according to the classical mechanics which we have. Okay, the classical mechanics. So now the potential energy function, okay, the potential energy we have whenever this vibrating diatomic molecule, the potential energy function under these influence of what we call a nuclear, which is vibrating, is parabolic actually, okay, which is a parabolic, and that potential energy actually which is given by V here, okay, which is given by V, which is equals to half into K into R minus RE whole square. Okay. V is equals to half into K minus, K into R minus RE whole square. So this we can write it as a simply half K x square also we can write. We can write it as a Kx square. X is nothing but the displacement for this atom. So we can write it as a half Kx square also we can write. So here K is nothing but what? It is a force constant we have, and Re is nothing but what? Re is the equilibrium internuclear distance. Equilibrium internuclear distance we have. And X here, whichever we have written, X is the displacement of the oscillator from the equilibrium position. Okay, from the equilibrium position, whichever we have. So here it is given the what we call the shape of that it is given, that is a parabolic potential energy curve is a parabola. So here it is given that in this form we have. So potential energy versus distance, whichever it is given, I'll draw here. Right. So potential energy versus distance. So this is a potential energy and this is the distance R minus RE, whichever we have. So this is going to be parabolic path like this. Okay, this is the parabolic path here. So now after this, if you consider, so far whatever we have studied is whenever this vibrating molecule, which is having the permanent, which is oscillating as a dipole, so which we have taken it as a what? Simple harmonic oscillator we have taken, and the frequency of vibrations which we have got it as a mu is equals to 1 by 2 pi under root of k by mu we have taken. And similarly, we have taken the what we call for this diatomic harmonic oscillator, the classical potential energy is given by what? Half into K into R minus RE whole square, which we have been taken. So now if you come to this, what we call quantum mechanical treatment. So in the case of the quantum mechanical treatment, in the previously, we said that whenever this vibrating diatomic molecule is going to be give certain energy, so that is in the form of what we call continuous you are going to be have, which we have written previously, whatever we have written. But actually, if you take about this quantum mechanics, so quantum mechanics, what it will tell is nothing but it is going to be have only discrete levels. That is nothing but it is going to be have a particular selected levels we are going to be have. That is in the case of the quantum mechanics for a molecules, it will uh, having certain selected energy levels it is going to be have. Okay, only the selected energy levels it is going to be have. So according to the quantum mechanics, it is going to be allowed certain energy levels for this harmonic oscillator. For this harmonic oscillator. So that is what we call we have like a 0 point energy which we are going to be called here. Okay. Otherwise, if you take in the case of this what we call class quantum mechanical treatment. So we know that in the case of the quantum mechanical treatment, we have E is equals to H nu. Understand? E is equals to H nu. Whatever this. We have E is equals to H nu we have. So here we can write that energy of the vibration, E nu we can say that. Energy of the vibration, we can write it as a H nu. So H nu here it is actually in the form of H nu that is oscillating, otherwise vibrating, whichever we can call, into we have this is vibrating or oscillating, we can say that nu frequency into nu plus half we can write. Okay, nu plus half here. Okay, so this E is equals to H nu vibration into nu plus half, whichever we have. So these gives the allowed energies for the harmonic oscillators. Understand? Allowed energy for the harmonic oscillator. And this nu is called vibrational quantum number here. This nu, whichever we have. This nu, what we are going to be called? This nu is called it as what? Vibrational quantum number. Vibrational quantum number. So it can take the vibrational quantum number nu can be take integral values, like nu is equals to we can have like a 0, 1, 2, 3 and so on. Can take a particular values like a 0, 1, 2, 3 values it can be take here. So here in this case, we have a special feature of the quantum mechanical oscillator, which is the what we call existence of a 0 point energy, which we calling it as a half H nu oscillations. 0 point energy, half what we call H nu oscillations. That is nothing but when we substitute nu is equals to 0 here, what you are going to get E is equals to, when we take 0, if you substitute here, we are going to get it as what? E is equals to H half H nu vibration or oscillation, whatever it may be. So nu is equals to half H nu vibration or oscillation we are going to be called, which we are going to be call it as what? 0 point energy we are going to be called. Suppose if you take nu is equals to 1, we are going to get a different value, like what you are going to get? 3/2 H nu vibration you are going to get. That means according to the quantum mechanics, it is going to be allowed only particular energy levels, not all, it is not continuous. So like that, we can have this what we call energy of this what we call vibrating diatomic molecule. Okay, vibrating diatomic molecule energy we are going to be having. We have written right directly E is equals to what is that H nu into half we have written. So in that case, if you substitute all these values, you are going to get this allowed energy levels we are going to get here. So now we will see the spectrum here. continuation, you'll get that whatever you got, G nu is equals to omega into what we got nu plus half together. So that you'll get in continuation of this one. So we'll see that spectrum here in the case of the diatomic molecule. Now we'll see the spectrum for this one. For this vector, nothing but observed vibrational rotational spectra, whichever we have. Okay. So now we'll investigate the expected spectrum for this diatomic oscillator. Okay, diatomic oscillator. Here we'll see the vibrational terms. Here, like centimeter inverse or meter inverse, we are going to be taking in terms of wave energy. We are going to be getting the terms of centimeter inverse, or which we can write as a G nu. G nu we can write here. Okay. The vibrational energy of the diatomic molecule, we can write G nu in terms of the wave number, which is equals to E by H nu we have. E by, so let's see, 1 minute. E by HC, not nu, is E by HC we can write. G nu is equals to E by HC we can write. So here we have a E value, already we have written. So if we substitute E value, that is what is that we have called nu vibrating, we have called, right? Nu vibrating. In the last we have seen, no? Nu vibrating by this C will get cancelled, H will get cancelled. Nu vibration by C into nu plus half we can get here. Because E is equals to previously we have got H nu vibrating into nu plus half we have got. In place of E, we have substituted this. What is that? H nu vibration into nu plus half we have substituted. So here in the denominator we have H. So if we cancel this, we'll getting it as what? H into H will get cancels. The G nu is equals to what we are going to get? Nu vibration by C into nu plus half we are going to get. Nu plus half here. Okay. So here, this nu vibration by C is there, right? So this nu vibration by C is the classical frequency in wave number unit. Okay. That is the classical frequency in wave number unit, and it is known as what we can call it as a vibrational constant. This nu vibration by C is there, no? So this one we will be calling it as what? Vibrational constant we can call. What is that we call? We can call it as a vibrational constant we are going to be called here. So generally this vibrational constant we can represent, otherwise we can denote with this omega. Okay, we can denote with omega. So therefore G nu, that is the what we call the vibrational terms, whichever we have, we can write it as what? G nu is equals to, we can write it as omega into nu plus half we can write. Omega into nu plus half we can write here. Okay. So here the values of this nu can be take like a 0, 1, 2, 3 and so on. Can take what? 0, 1, 2, 3 and so we can take. So if you substitute, suppose 0, if you substitute, what you are going to get? This G nu value? G nu value you are going to get as half omega you are going to get. Suppose if you substitute similarly, like 1, if you substitute, you are going to get it as what? 3 by 2 omega. And if you substitute 3 you are going to get it as what? 5 by 2 omega, comma, like this 7 by 2 omega, and so on you are going to get. Okay, so on you are going to get. That is, we have a series of equidistant discrete vibrational levels you have. If you see the difference between this one, 3 by 2 omega to 1 by 2 omega is half omega you are going to get. Similarly, if you see the difference between the 5 by 2 omega to 3 by 2 omega, again, half omega you are going to get. Similarly, if you take the difference between the 7 by 2 omega minus 5 by 2 omega, you are going to get again half omega. That means we have a series of equidistant discrete vibrational levels you are going to get. In the case of the spectrum, as we observed, what you are going to get? We are going to get a series of equi-spaced or equidistant discrete vibrational levels you are going to get here. Okay. The common separation between them is what we have? Omega is there. So suppose if you see the separation distance between them, so the figure if you see like this, so we have equi-spaced discrete levels. For nu is equals to 0, what we have got? Half omega. For nu is equals to 1, what is that? We have got 3 by 2 omega. For nu is equals to 2, it is 5 by 2 omega. For nu is equals to 3, it is 7 by 2 omega, like this 9 by 2 omega for 4 here. So, as if you take the frequency here, we'll be getting these values. So, the distance between them is equally spaced. Okay, equally spaced here. Okay. So, here, when a transition takes place between upper level, okay, when an upper level, say that the upper level as a nu dash. Understand? The transition takes place from the upper level nu dash and a lower level nu double dash if you take. What is here? When a transition takes place between an upper level nu dash and a lower level nu double dash, here the wave number of the emitted or absorbed radiation. Understand? What we said that whenever it is going to be absorb certain amount of energy, it will be moved to upper level. Otherwise, whenever it is coming from higher energy level to lower energy level, it will be radiates. So here like this, whenever the transition is going to take place between these upper level and the lower level, the wave number of the emitted or absorbed, because whenever it is emitting, when it is moving from higher to lower, whenever it is absorbing from lower to higher. So the wave number of emitter or absorbed radiation, we can call it as a nu, we can call, that will be equals to G nu dash minus G nu double dash. So here what is happening? The transition is taking place between the upper level nu dash to lower level nu double dash. So therefore, so if you elaborate this one, so what you'll get? G nu dash is nothing but omega into nu dash plus half we have. Similarly, G nu double dash is nothing but omega into nu double dash plus half here. Okay, half. Understand? So, for a harmonically oscillating molecule of dipole moment M, okay, for a harmonically oscillating molecule of dipole moment M, if you take here, dipole moment M, if you take, the matrix element is found to be non-vanishing, which is nothing but dm by dt, which is not equals to 0. And this delta nu means which may be plus or minus 1 only you have. Delta nu you are going to have only plus or minus, you have 1. Okay. So that is nothing but for the vibrational transition can only occur when the molecule has a permanent dipole moment. molecule has a permanent dipole moment. Suppose if it doesn't have the permanent dipole moment, the dm by dt value is going to be 0. So you are not going to get any vibrational transition. So the vibrational transition can occur only when the molecule has a permanent dipole moment, which changes with the distance. The selection rule is given by what? Delta nu is equals to plus or minus 1. So it may be plus 1 or minus 1 you are going to be have here. Okay. So here, if you take, we said that nu dash is the upper level we have called, nu double dash is the lower level. So we can write nu dash is equals to nu double dash plus 1 we have. Why? Because the selection rule, what we have, the change should be plus 1 or minus 1. So therefore, we can write nu dash is equals to nu double dash plus 1 we can write here. So here, since we know that nu dash is the greater than nu double dash. Why? Because nu dash we call it as what? Upper energy level we have, upper level we have called. Nu double dash is the lower level we have called. So automatically, always it will be nu dash is greater than nu double dash it should have. Okay. And if you take the spacing between this what we call vibrational levels are considerably larger than the spacing between the rotational levels of a molecule. Okay. So as we seen already rotational level also. So generally the spacing between these vibrational levels is larger than the what we call spacing between the rotational levels of a molecule. Okay. So this is what we have what we call spectrum or observed vibrational rotational spectra. So as in your book, it is given in terms of what we call a figure. Right. So this is what the spectrum which we can observe here. Okay. So it is shown in the form of what we call lines. It has been shown in your book. Now we'll see the fine structure. Okay. Fine structure of this what we call vibrational spectrum. We'll see the fine structure. That is which it has been mentioned like vibrational core structure. It has been mentioned. So we have like a fine structure of infrared bands, that is nothing but molecule as a vibrating rotator. Okay. Molecule as a vibrating rotator. So here, if you see the fine structure of this, what we call vibrating rotator, molecule as a vibrating rotator, we can call. So fine structure of this infrared bands means each band it is consisting of again divided into what we call a different levels. It has been divided. So in the case of this near infrared spectra of molecule of bands, because this vibrational spectra is going to be observed in which region? Near infrared region only it is going to be observed. So in the near infrared spectra of molecules, it is consisting of what? Like a bands, it is going to be consisting. Is going to be consisting of a form of a bands, okay, not lines. And this each band being composed of closely spaced, otherwise closed lines arranged in a particular manner. Okay, this band again it is subdivided. Otherwise, we can say that it is consisting of what are closed lines arranged. Okay, closed lines arranged here. Okay, in a particular manner. So in the series of lines which are not equidistant actually. So these are not equidistant. So in some cases, what we call some lines are going to be misses. So the missing lines, which we will be calling it as what a null line or a zero gap, we are going to be called here. Okay. So the observed fine structure in infrared band, which suggests that vibrational transition. Okay, vibrational transition, the molecule also changes its rotational energy states. That means whenever it is transition, vibrational transition takes place, here also going to be changes, what we call rotational energy states also it is going to be changes. Therefore, it must be treated as a vibrating rotator actually. So whenever we are studying about the fine structure of this vibrating uh, rotator if you take, so we will be treat it as a vibrating rotator we have to treat here. Okay. So now if you take the this uh, as a simple harmonic oscillator we have to consider, and as well as the what we call we have to consider again anharmonic oscillator also we have to consider. So that is nothing but the vibrating rotator would be given by the sum of the term values of the anharmonic oscillator and the rigid rotator. So that is the reason why we can write this as a combination of G nu, which we have already studied. And also in addition to that one, we have f of j. So which is an anharmonic oscillator. It is a combination of vibrating rotator is a combination of both what we call terms of the anharmonic oscillator and the rigid rotator, whichever we have, G nu plus Fj we have. So already we have seen that G nu value already we have calculated. So which we can write it as omega E into nu plus half, okay, minus here we have additional term omega E x E into nu plus half whole square plus B into j plus 1. Okay. Plus G nu we have written, the combination of this. So that will be equals to omega E into nu plus half minus omega E x E into nu plus half whole square plus B into j plus 1 we have. Okay. So here what we have got, one B term we have got. So already we have uh, seen this B value, its value is equals to h by 8 pi square IC. Okay, B value is equals to what we have, h by 8 pi square IC. So which also can be written as, this value can be written as h by 8 pi square. In terms of reduced mass, if you take, this will be mu into R square C. You are going to get here. Okay. Mu is nothing but what? Reduced mass of the molecule you have. Okay. So one thing you have to observe here in the case of this vibrational course of structure, that is nothing but we have to take into account vibrational as well as the rotational changes also we have to take into account here. So in the case of this what we call the rotational levels, with the similar spacings associated with each vibrational level. Suppose if you take an example, you will have a what we call for one vibration, for one vibration, you will be having 50 rotational levels. 50 rotational levels. This is in the case of the example of a HCl molecule. Understand? That is nothing but whenever we are going to be study about the vibrational energy levels, you will be having the rotational also. So suppose if you take the example of this what we call HCl, so we will be having 50 rotational levels for a single vibrational level we have. Okay, for vibrational level. That means we have to take both vibrational and rotational into consideration we have to take. So whenever a transition is going to be occur, okay, whenever the transition is going to be occur between the two vibrational levels, so it will be have accompanied by number of transitions between the two corresponding rotational and as well as what we call vibrational sets. Okay, because if you take one vibrational transition, under that one vibrational transition, we have like 50 rotational levels will be there in the case of the HCl. So whenever a transition between the two vibrational levels would therefore be accompanied by a number of transition between the two corresponding set of rotational levels. అంటే ఏముంటుంది ఇక్కడ ఒక వైబ్రేషన్ ట్రాన్సిషన్ జరిగినప్పుడు you will be having accompanied by some rotational transitions also. So along with vibrational, you will be having what we call rotational transitions also will be there. So that is the reason why you will be able to see like a band. So actually that band is consisting of what closely spaced lines you are going to be have. Okay, some closely spaced lines you are going to be have. So this vibrational transition whenever it is occurring, so it will result a number of lines in a band. As we said, that band is consisting of what? It is consisting of a closely spaced lines you are going to be have. So whenever this vibration transition is going to be takes place in like a band, so in that band we'll be having a number of again subdivided lines you are going to be have. Okay, these lines would form two branches of distance lines you are going to be have. Okay, so now we'll see here that in the form of figure, if you see, vibrational rotational structure, if you see here, so for nu is equals to 0, for 1, 2, 3 like this. So this is the RE. Okay, so we'll find the shape of this potential curve in this manner. Okay, as new value is increasing, you see new value initially we have 0, then 1, 2, 3 like this. So as new value is increasing, the equilibrium internuclear disk separation RE, okay, and hence the moment of inertia of the molecule also increases as the new value is going to be increases. So that the rotational constant B, whichever we have seen here, so the B value is going to be decreases. The B value is going to be decreases. So which will determines the what we call spacing between the rotational levels is different for different vibrational series we are going to be have. Now we'll see this B value. B value also can be written as B is equals to H by 8 pi square mu C into, we can write it as a 1 by R square into mu. This is the average value. So here 1 by R square bar is there, no? So that is the mean value of 1 by R square in the vibrational state. Okay, 1 by R square dash is there. That is the mean value of 1 by R square in the vibrational state nu actually during this vibration. Okay, so it can be shown that the rotational constant B nu is the vibrational state we have. So that given by B nu actually. B nu is equals to BE minus alpha E into this nu plus half, and so on you are going to get here. So this alpha E is a constant which is depending upon the shape of the potential curve. This shape of the potential curve you are going to be have. Okay. So therefore, whichever the equation which we have written G nu plus f of j, here we have written omega E plus nu into 1 plus half 1 by 2 minus omega E xc. This nu plus half square plus b into j plus 1 is there. Here it is written, no? So if you take for two different levels like a b dash and b double dash, if you take, it is going to be changed its value. Okay. So and coming to this right. So we'll have this delta nu here. Okay. Delta nu is a selection rule. Delta nu is equals to plus or minus 1 or plus or minus 2 or plus or minus 3 and so on. Okay. Whereas delta j is equals to only plus or minus 1. Okay. Delta nu can be very like a different values like plus or minus 1, plus or minus 2 means that means the transition between the two different levels you may have like 1 or 2 or 3, whatever it may be, delta nu. Whereas delta j is equals to you have only plus or minus 1 as we have seen in the previous one. Okay. So for j, both the transitions, what are the transitions? Like a plus or minus 1. Plus 1 or minus 1 are now applicable in the case of the absorbed version. Okay. So because the two j levels involved, okay, the two j levels involved now belong to two different vibration levels. Okay. So for a given transition, that means for a vibration transition, actually, we are talking. Okay. So for a given vibrational transition, the rotational transition is delta j is equals to plus or minus 1. Already we have written. So as we have like a delta j is equals to what is that we have selection rule? Plus or minus 1. So either you have a plus 1 or minus 1. Two values you have. Okay. So in this case, for the value of delta j is equals to 1, that is for plus 1 actually, plus 1, which will be giving some set of lines, which we are going to be call it as a R branch we are going to be called. What is that? R branch we are going to be called. Similarly, for this delta j is equals to plus 1 gives one set of lines called R branch, while the rotational transition for delta j is equals to minus 1, another case. Minus 1 gives the other set of lines, which we will be calling it as a P branch, which we are going to call it as what? P branch. ఇక్కడ మీకు ఇందులో డైరెక్ట్లీ దే హావ్ గివెన్ దట్ P branch, R branch అని ఇచ్చింది మీకు ఇందులో బుక్ లో. So you won't understand directly if you go. So for delta j is equals to plus 1, the one set of lines called R branch you are going to get. And for rotational transition, delta j is equals to minus 1, you are going to get another set of lines, which is calling it as what? P branch we are going to be called here. Okay. So all the lines of both branches forms this vibrational rotational band you are going to be formed here. Okay. Both you are going to be form this vibrational rotational branch you are going to be formed. So if you write here this total new value, whenever it is going to be coming from one level to another level, like new value if you write, so we know that we have G nu plus f of j. So here we have for one level it is G nu dash plus f, it will be nu dash comma j dash, and minus we have G nu double dash another level plus f of nu double dash j double dash. So here we solve this, we will get some value here. So for this, we can see the R branch as well as the P branch. Suppose if you see the R branch, means different. When you are going to get, when delta J is equals to +1, you are going to get this R branch you are going to get. So for R branch, delta J is equals to, if you take, it will be J dash minus J double dash, which is equals to +1. Because R branch, when you are going to pairize, when delta J value is equals to +1. So that J dash value is equals to what you are going to get? J double dash +1 from this one. Okay. J dash is equals to, you are going to get J double dash +1. So we obtain the lines of R branch with the wave number, like a wave number, if you take, it will be new R branch as new R. This will be equals to nu naught plus B dash new to J double dash +1. Next, J double dash +2. Similarly, minus B new double dash J double dash into J double dash +1. Okay. So if you solve this, you'll get you are going to get mu naught plus 2B mu dash plus, you get the 3B dash mu minus B mu double dash plus B mu dash minus B mu double dash into Q dash square you are going to get. Okay, this you are going to get for R branch. So as it is written in your book here. Okay. So for this, if you see the transitions, this is for nu dash is equals to 1 if you take. So it may have like a 0, 1, 2, 3, 4, 5 levels. 0, 1, 2, 3, 4, 5. And similarly, we'll take nu double dash is equals to 0 if you take. So this also 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, 5. So 0 level 1, 2, 3, 4, and similarly have 5 fifth level for this 0, 1, 2, 3, 4, 5. That means actually you can able to see what we call one single level you are able to see, but actually you will be having these many number of different lines you have. And again, the transition is going to be takes place according to this what we call selection rule. Like if you take the transition, so 0 to 1. The difference is how much here? 1 we have. Right. Similarly, suppose it can be moved from 3 to 2 in this 3 to 2. So what is the difference in this case again? 1 we have. And similarly, it can be moved from what we call 4 to 3 also. In this 4 to this 3. Again, the difference is how much? 1 we have. Like this fifth level to again fourth level from here. Fifth to fourth level. How much difference you have? Delta J is equals to 1 we have. Similarly, again, in this side also, we can able to move from 1 to 2 or like 2 to 3 or 4 to 4. For new double dash is equal to 0 means you'll have the difference like 1 you have. So this is what R branch we are going to be called. Similarly, we'll have a P branch also. This one is somewhat complicated. So similarly, you'll get have another which we call it as what? P branch, right? P branch. So when we are going to get P branch, the value should be equals to delta J is equals to how much? -1. Delta J is equals to -1. That means delta J value is equals to, you are going to be have for two different levels, J dash minus J double dash is equals to -1 here. So we can write here J dash is equals to what we can write? J double dash -1 we can write here. Okay. So we will obtain this, what we call P branch with the wave numbers. So similarly, the equation for P branch also we can write, which is can be written as a new P is equals to, I'm writing directly, which actually you are going to get what we call nu naught minus P nu dash plus P double dash nu into J double dash plus, what is that? B nu dash minus B nu double dash and J double dash square. This is what the equation which I have written directly. This is what we call it as a P branch you are going to be called. Okay. So J double dash is the lower rotational quantum number. J dash is the upper rotational quantum number we have. Here we have no J double dash. J double dash is the lower rotational quantum number and J dash is the upper rotational quantum number we have. So J double dash, it can takes the values like 1, 2, 3 and so on up to J double dash we have. Okay. And it cannot be 0. It cannot be 0. Why? Because J double dash is equal, sorry, J double dash is equal to what we have? -1. Okay. -1, which is does not exist. So the P branch consisting of what? Like a P1, P2, P3 lines we have. In the case of the R branch also we have seen like R0, R1, R2, R3. And we have, and the P branch we have like the notations whichever we have shown here. So these notations, this one, only we have a difference of 1 we have, which is known as a P branch here. This is a P branch we are going to call. And the RHS also here we can show, in which it can be have a what we call 0 level also. R branch we have 0 level. That is nothing but the transition can take place from 3 to 3 or like that you are going to be have. Similarly, we have 0 to 1 or 2 to 3 or 4 to 5 transitions in this one. We will be calling this as the R branch. In this case, we'll be getting R0, R1, R2, R3, R4, whatever it may be. So in this case, we are having only P1, P2, P3, P4. Okay. So in the case of the R0, if you take, this can be have a 0 to 1 level like that we have. So this is about the P branch and R branch. So this is what we can call the vibrational force of structure we are going to be called here. Okay.